Hey everyone, and welcome back. So today we're going to tackle a topic that I know a lot of you find a bit tricky, the reactivity of metals. But don't worry, La, by the end of this quick explainer, I promise you'll see it's actually super straightforward.
All right, so to really get why this chapter is so important, let's kick things off with a big question. Have you ever thought about it? How do we actually go from a simple rock, just something we dig out of the ground, to a shiny car door? Or even your phone or the spoon you used for your breakfast this morning? Well, the answer to all of that, it all comes down to understanding metals. So to get that answer, we've got to know where metals even come from. See, they all start out as minerals, deep inside the Earth's crust. But here's the key thing you have to remember. Not all metals are created equal. Some are really, lazy and chill, while others are, well, they're super active. Okay, so what exactly is a mineral? Well, don't let the formal definition scare you. Simply put, it's any solid element or a compound that's just naturally there in the ground. So it could be a pure element like gold, the shiny nuggets people find, or it could be a compound like this reddish rock called bauxite, which is what we use to get aluminum. All right, let's get to the main event. This is probably the most important part of the whole chapter, the reactivity series. Honestly, the best way to think about it is like a power ranking for metals. Yeah, kind of like a football league table. It tells us which metal is the sifu, the boss, and which ones are just followers when it comes to chemical reactions. So what's this whole series about? It's actually really simple. It all boils down to just one thing. How badly does a metal want to react with oxygen? That's it. The metals at the very top, they're super kanchong, very eager to react. Meanwhile, the ones at the bottom, they really couldn't care less. Right at the top of our power rankings, we have the champions, the superstars of reactivity. I'm talking about potassium, sodium. These guys are so reactive, they will literally burst into flames if they even touch water. No joke. We actually have to store them in oil just to keep them calm. Okay, moving down the list, we've got our middleweights. Now, these are your everyday hardworking metals, like iron and zinc. They'll react, for sure, especially if you heat them up, but they need a little push, a bit more encouragement. They're definitely not as dramatic as the champions at the top. Okay, so here it is, the complete list. Now this is the part you really need to memorize for your exams. So take a good look, let it sink in. Wait a minute. Do you see something kind of weird? Look at those highlighted ones, carbon and hydrogen. Hang on, they aren't metals. So what on earth are they doing here? Well, their position in this list is the key to, well, everything, and we're about to find out exactly why.
I bet that's the question on everyone's mind, right? And it's a really good one. So here's the deal. Carbon and hydrogen are in this list to act as a kind of dividing line, a benchmark. Think of it this way. Any metal you see above carbon is considered very reactive, and any metal below it is less reactive. And this one simple line, this is what tells us exactly how to get these metals out of the rocks they're found in.
So you might be wondering, how do scientists even know which metal is more powerful than another? They don't just guess, They actually make them race. Yup, it's basically a great big race to see which metal can react with oxygen the fastest and with the most energy.
So how do we actually prove this ranking is correct? Well, with a pretty cool experiment that you might even get to do in your school lab. It's actually quite simple. You just take some metal powder, heat it up until it's really hot, and then you give it a blast of pure oxygen. After that, you just sit back, watch the fireworks, and see how genes, how fierce the reaction is. And trust me, the difference is massive. You can see it straight away. A highly reactive metal, something like magnesium, it just burns with this blindingly bright white light. It's super spectacular. But then you try a less reactive one, like lead, it just glows dimly, kind of like a dying ember. And this huge difference in vigor, that's exactly how we build the reactivity series, from most reactive to least. Okay, now for the big payoff. This isn't just about theory for your exams, okay? This is where it gets real. Let's see how this reactivity series is actually used every single day in massive industries to get the metals we need to build our modern world. So this table right here, this is the key takeaway. A metal's position on the series tells us exactly how to get it out of the rock. Remember our special guest, carbon, our benchmark? Well, for all those super reactive metals above carbon,
We have to use a really powerful method called electrolysis. But for the metals below carbon, we can just use carbon itself to do the job. And what about the super lazy ones at the very, very bottom, like gold? Well, we often just find them hanging around as pure elements. Pretty cool, huh? Now, let's talk about one of the most important metals in the world, iron. You know, for our cars, our buildings, everything. Well, the hero of the story for getting iron is carbon. And why is that? It's simple, because carbon is more reactive than iron. So inside this giant oven called a blast furnace, we basically use carbon to steal the oxygen away from the iron ore. And it's basically a simple 4-step process. So step 1, we charge the furnace. That just means we dump all the ingredients in at the top. That's the iron ore, something called coke, which is basically our carbon and limestone. Step 2, we blast super, super hot air in from the bottom. Step 3 is the reaction. Inside all that intense heat, the coke gets to work and pulls the oxygen away from the iron ore. That process is called reduction. Now, the limestone is also really important. It cleans up all the impurities, like sand, and forms this molten waste called slag. And finally, step 4, separation. Molten iron is heavier, so it sinks to the bottom, while the lighter slag floats on top. Then we can just tap them off separately. Done. Okay, people, let's wrap this up with a quick cheat sheet for your exams. These are the key points you absolutely 100% must remember. So listen up. Go on, feel free to screenshot this for your notes. Okay, number 1, and this is the most important. You must memorize the order of the series, no shortcuts. Number 2, a very common exam question. In that experiment we talked about, you always heat the metal first before you supply the oxygen. Why? Because you got to get it hot and ready to react. And number 3, just remember the golden rule. A more reactive element will always, always steal oxygen from a less reactive one. This simple rule explains everything. It's why carbon can reduce iron oxide, but it can't do anything to aluminum oxide because aluminum is way higher up the series and way more powerful than carbon.
And please, please, don't get caught by this common mistake. When your exam paper uses the word mineral, please don't just think of shiny diamonds and rubies. In chemistry, even a boring-looking brown rock like hematite is a super important mineral because that's where we get our iron from.
So, look, if there's just one thing you take away from all this today, let it be this. The reactivity series isn't just another list you have to memorize for an exam. No way. It's the fundamental rulebook. It's the recipe for how we build our entire modern world, from our cars to our skyscrapers. Everything starts with this simple power ranking of metals. And I'll just leave you with this final thought to chew on. We saw that carbon was basically the hero of the Iron Age, right? But it's just not powerful enough for modern metals like aluminum, which needs crazy amounts of electricity. So as we look to the future, I want to ask you, what do you think will be the next big thing? The next clever chemistry trick? The new carbon that's going to help us build the world of tomorrow? Something to think about. Thanks so much for joining me today.